So the volumes of solids with disks and washers. Looking up, is it disk with a C or disk with a K? The answer is it could be both. I think I wrote C because that's typically when you have an actual disk. But either way works. Let's go. So a reminder from the cross sections video, and I'll show you this. How do you find volume? You got this generic equation: volume equals the integral of area. Because you integrate a 1D line, you get a 2D area. You integrate a 2D area, you get a 3D volume. I like to think it like that. So here's your generic formula where it's A. Now, what happens if we're not looking at our cross sections shape this time? We're going to be looking at disks. And I want to show you what these. All right, so here's some animations. I want to show you what it looks like. So we did cross sections. Now what we're doing here is we're going to be revolving something around an axis, like maybe around the x-axis or y-axis to create our volume. So instead of just putting shapes as cross sections here, we're revolving. And so here's some examples of what this would look like. On the top stuff is like we call it the disk method. So we create you're just rotating around here and it really creates circles or disks. So like especially this one on the right here. You're taking this curve, you're rotating it, kind of looks like a vase, and then you're filling this up and it looks like a bunch of circles. We call the disk method of calculating this volume. Now we'll also get to the other things like what if there's a hole inside? That'll be the washer method. So you end up having it's kind of like a disk, but then you have a disk inside that ends up being a hole. So these are the kind of shapes that you will be creating with today's work. And as a reminder, to find volume in the generic equation is the volume is the integral of the area. You got to find your limits and you got to find the shapes. Well, the shape is a circle. So our disk formula, let's start with there. This is without the hole in the middle, it's just filled in. And so like this shape right here, our disk formula is going to be pi times integral from a to b of r squared. Very similar to the generic volume formula. I mean, the area of a circle is pi r squared, right? So area of a circle is pi r squared, and you basically have pi r squared right there, replacing the area. Except we put the pi on the outside because it's a coefficient. We can put it inside too. It doesn't matter. So it's really the same as the cross sections formula. Just it's represented as a disk formula. And I made this note right here. They're like cross sections, but they show up so much in AP Calc. Like we treat it differently when we're teaching this as a disk formula, but not really different. So think of it as just this, except same equation. Just pi r squared. It's a circle because you form circles. So same rules of solving it as before. So let's take up an example like this one. I want to set up an integral for the volume of this solid revolved around the region by y is x squared, y is 0, and x equals 1 about the x-axis. Sometimes, the challenge is you got to sketch these out if there's no picture. You got to find your limits. So here's the picture. This is the x squared. This is x equals 1, and y equals 0 would be the x-axis. So this area, we're rotating it around. You'll get this kind of washer shape. So it's like a cone that's going to funnel out. But again, imagine it's like filled in. So it rotate around, whoosh, and like you kind of have this mirrored effect there, and just do a bunch of circles, smaller and smaller. Really hard to draw. I'm bad at that. But what would that look like? Well, our limits here are going to go from 0 to 1. So my volume is going to be from 0 to 1. And, oh, don't forget that pi in front. I almost did. And then it's going to be r squared dx. So what is my r? Your r is your radius. Now it's not like the semicircle one. It was just half that radius. We can just half of this whole distance. The radius of this circle is from the axis of revolution to this function here. And that function is x squared. So I can just say it's x squared. So there's my volume function. And I'm going to clean this up a little bit, and I'm actually going to solve it from 0 to 1. It'll be x to the 4th dx. You integrate, you get pi x to the 5th over 5 from 0 to 1, which is going to be pi 1 to the 5th over 5 minus pi 0 to the 5th over 5. That's all zeroed out, so I get pi over 5, because 1 to the 5 is just 1, and that's my answer. So there you go. Find your limits. Typically, it's just going to be whatever that top function is, and then your axis of revolution. All right. Hey, maybe now one of the challenges, maybe I revolve around the y-axis right here. So I don't have to revolve around the x, I can revolve around the y. And what to say I had bounded in quadrant 1, and so that's 1, and that's 2, and that's 3. This is quadrant 4, forms kind of a C shape. So quadrant 1 by x squared, x equals 0, and y equals 4. Well, if I were to, let's say if I draw these out. So I'm going to say x equals 0 is going to be the y-axis, so it's going to be this line. Y equals 4 is going to be this line up here. And then I have the function y equals x squared. Okay, so it's a parabola, and I'm going to remember 1, 1 would be the point, and 2, 4 would be a point right here. Plotting a few points, I want to make sure I do a good job drawing it this time. Or a better job than normal. Oh, that's awful, but it doesn't matter this side. I don't know, my tablet's kind of small. I got a wrist. My elbow down, I can draw nicer. No, it's not going to work. Yeah, who cares? I'm not even worried about this side. I'm worried about this side right here. So the area that's bounded by all of those is going to be what is over here in this area, right? So that is going to be revolving around this y-axis. Think of it's going to be making a cup. But it's going to be like filled in right here. So it is going to revolve around this way, kind of be doing shapes like, this, doing our circles, kind of like that. So what's it going to look like? Now, I'm not integrating my volume. I'm going to have to, since I'm rotating on this axis, I'm actually not going to be doing a dx functions. We're going to rotate with respect to y. So I have to change my expectations when it's on this side. Just like when you try to do the area between two functions and it was sideways. So I'm going to be going from 0 to 4, the y values, not 0 to 2, the x values. And the length of this is whatever the length of this function is. Now that's y equals x squared, but I have to make this an x equals function. So y equals x squared, and then I am going to square root both sides. I'm going to get x is equal to plus or minus square root of y, right? Well, this is the positive side right here for this function. So I can say it's x equals positive square root of y. So now I have square root of y squared. Oh, don't forget the pi r squared. So I can do that math, pi from 0 to 4 of just y, because the squareds cancel out. If I wanted to do that work, it's y squared over 2 from 0 to 4, which is going to be pi times 4 squared over 2 minus 0 when you plug in that. So you get 16 pi over 2, which is just 8 pi for your answer. All right. Try some other examples here. Oh, before we get into that, let's say washer formula. So hey, what about if there's a hole in the middle? Like I saw with that shape back here. This one, you kind of got a hole in the middle right here. So it's kind of like the disk method, but then we also have like a disk inside that cuts it out. The way we write it is just like this. Pi times the integral from a to b of big R squared minus little r squared. So big R represents the outer radius and little r represents the inner radius. So I'm going to say, another way I like saying this is big R is going to be farther away. And inner R is going to be closer. Okay? Like thinking about it like that, farther away, inner radius is closer. So it's not necessarily going to be top minus bottom. Got to watch out for that. All right? So big R squared minus little r squared. Now it's not, and which is not the same thing as big R minus little r squared. Those are not the same. Don't do that. That's not how that works. So let's take some scenarios. Oh, we don't need that. That's disk method. Let's take these two. So we're going to rotate the area between the curves. So I'm rotating on the x-axis right here. If you're rotating this shape, there's two curves right here, negative x equals 5 and y equals 1. I have two boundaries of -1 and 1 for x. So if I rotate this shape, what ends up going to happening is I'm going to have like, this is going to be like the filled in shape. You get this like circle, ooh, goes around like this. Kind of rotates. But you're also going to have this like inner hole right here as a circle. So it's this disc on the outside with a disc hole in the middle. Maybe you can see that. I don't know. So what I have to, if I'm setting this up, air volume is equal to pi. Okay, my limits are still -1 to 1. But it's the big R squared minus the little r squared. And my big R is what is outside. So the functions that are outside here is if my axis is this line right here, which functions farther away, it's this one on top, it's the parabola. So I'm going to say my outer is negative x squared plus 5. And my inner function is going to be this line y equals 1. So it'll be 1. Boom, set up. Plug it into a calculator or whatever, you're done. That's it. Let's try this one over here. So it might be, this one will behave a little bit differently here. You're rotating. You have two functions, y equals 3 and 2 over x, and x equals 5 is one boundary. So I want to rotate this one around the x-axis. If you rotated it, it'd probably look like this shape, and you're going to get this. It's going to be like the outside circle, and like the inside circle is going to be like a hole, like try to do a dotted hole like that. It's like inside, right? Inside hole right here. So what's that going to look like? And then like this is going to be like a full out. It's going to be pretty much just filled in right there. Oh, howdy, dog. Anyways, what's that shape going to look like? Okay, my volume equation, I'm going to set this up again. So it's going to be pi. Now, so my outer limit's 5. And the inner limit, like where is that point? Not specified. So I can set these two equations equal to each other to find out. Okay, so multiply by x on both sides. Divide by 3. X equals 2/3. You might need to do a little math. Now it's going to be the outer squared minus the inner squared, dx. So our outer is whatever functions farther away from this axis. That's going to be this line. Like what's farther away right here? It's this line. And that line is 3. And that means this thing is going to be the inner. So it's 2 over x. And there's my setup for my equation. All right. So it's whatever outer minus inner, farther away. Now, this is where it gets trippy. What if we're not rotating on the x or y axis? We're not rotating on the axis. You have a shift, like I'm rotating on like y equals 1 or y equals -2. So I think this is probably the weirdest part of this. Think about it, think about it if like I move my axis up, think of it as the same thing as just shifting my graph like up one. It's the same thing as shifting my graph down one. So shifting the axis up is like shifting the graph down. So what I do is what I just say is add or subtract the opposite. So do the opposite. If this is +1 for the axis, subtract 1 from the functions. So it's like taking the functions and shifting one down to everything. And that'll give you your shape. I mean, because basically we're shifting on this axis instead of this. Like if I shift on this axis, just rotate right here. It might be like touching at the vertex, right? But I'm not shifting right there. I'm shifting at this axis. So the mirror would happen way up here. It was between these 2 points or whatever. Oh no, it's like right here, right? With that hole. So this is filled in. So you got this like, so you got a bigger gap right here. Okay. So the easiest thing I would say is to think of this as you're shifting it by the opposite. So here's what I mean. My volume is going to be from -1 to 1 for over here. And which is farther away from the axis? That line is farther away. So let me set this up, minus whatever squared. And we would say, oh, the line's farther away. So x minus 2 is farther away. And this is -x squared, right? But since our axis is shifted up 1, subtract 1. Done. I set up the equations. I'm done. That's the way I think about this. Some teachers might do it differently. But sometimes they get like a 1 minus this thing here. And really, all you have to have is the difference between those two because you're squaring it. It's always going to be positive. Yeah, remember, you're squaring these. So it should all, forgot the I. Of course. Yeah, it's always going to be positive when you're getting these volumes because you can't have negative volume. And in these cases, you're squaring things. So let's try this one right here. So I'm going to do my volume. Okay, I'm going from 0 to 2. It looks like that. I'm just going to believe it. And so I'm shifting my axis down 2. It's going to be the outside squared. Oh, and there's a pi minus the inside squared. And my outside is going to be farther away. It's actually going to be this line again in this case. So it's going to be 2x, and then the other one's going to be x squared. And since I am shifting -2 for my axis, all of these things are shifting up 2. And you have to do +2 to each of these being squared. You can't just do +2 on the outside. That's where they get you. So there you go. I think that's good practice. I don't need to do the sideways. Oh, shell method. We're not worrying about that one right now. See you later.